like I can 15 without a KSP.
Yeah.
Because
Well,
I needed
15, the KSP is here. Right there. Number 5.
Oh. Never mind. Then, yeah, we would have had it somewhere in there.
Yeah, either in the exam or I'd put it on the board. So you would need the KSP.
And then I had issues with solving 16 in general. I didn't know what to do with the pH. Because you give us an initial pH.
Well, 16 was which problem again?
Calculate the solubility of calcium sulfate with a KSP of 9.1 times 10 to the negative 6 at a pH of 3.0. Oh.
So at pH, for number 16, at pH of 3.0 means what? Means the pH initial or pH final? Right.
So something minus by x is equal to
Yeah, something like that.
And things to go, but then so you have two equations to work with: the calcium sulfate and the calcium sulfate, the CH and SO4 and the CH plus and SO4, and then just go with reverse of the acid. Like H2SO4 plus H2O plus H2SO4. There you go. But reverse this, you can cancel the sulfate ions. And then so you have the KSP times the K, but then if you reverse ions, right? What? Alright, I got it.
Then you gave us a Ka of HSO4 too, which I'm assuming we would need.
Do you know what do you know what KSPA is? Let's start with that.
Acid, right?
Do you know what KSPA is?
KSP and Ka. Dissolving multiply KSP and Ka.
Solubility
in acid?
It's solubility in acid, so it's a KSPA problem. You have to determine what KSPA is first. And so the KSPA is the equation. So, the KSP equation, and then you look at what's attacked by acid. That gives you the KSPA equation. Okay. So once you have the KSPA equation, then it's just a regular ice table.
Okay.
So you have to look at what in the KSP equation is attacked by acid, and then you could do the combination method. You could always do the simultaneous method for these as well.
Okay. What's the distinction when you can't use the combination or triprotic? Or is that or triprotic acid? Because the combination ends up just not. Like you end up getting too much.
All right. What the question is, when can you use the combination method? Does somebody have the answer to that?
When you're dealing with the KSP and Ka.
No, it's not exactly that. Because you could use the combination method for KSPF. You guys know KSPF? KSPF.
No, that's KF.
Oh, somebody tell me about the combination method where I used it. In what examples did I use the combination method? What was the combination method?
Sulfate.
You look nice.
And I think you dissolve that in.
Well, let's do since the class has started. Let's just do general questions here rather than individual questions on a one-by-one basis. All right, yeah, the first thing is the rough draft is due today. You turn that in. If you haven't turned in your qualitative analysis, make sure you get that one in too. Oh, dang. That's impressive. I haven't determined yet. At least 5. And the homework is due today. All right, so we have time at the beginning. So what are the questions you guys have?
when determining
Okay, go ahead.
so when determining which anion would precipitate first, we would both find the KSP for each compound, and whichever requires a lower Ag, or the lower cation concentration will go first, right?
Right.
Okay.
That's correct. So the question is, which one precipitates first? It's the one that requires less precipitating agent. That's the one that precipitates first. Uh-huh.
How can we get AgCl to dissolve?
How can you get AgCl to dissolve?
Yeah, besides mixing it with ammonia.
You could. All you have to do is do a Le Chatelet shift. You know, we were talking about this yesterday. What does the uncommon ion effect do? Sodium nitrate. Did we talk about that?
The uncommon?
Right. Which one is the most soluble in? Lead. What was it that we were looking at yesterday? Lead. Well, do you guys remember what we were looking at yesterday? Lead to iodide. What was it more soluble in? Water or sodium nitrate? Why was it more soluble in sodium nitrate?
Due to the ion properties. The ion or the density.
No, we don't want to explain it like that. Explain it in other terms, the terms that we had earlier.
The activity of the ion versus water.
Okay, then tell me what specifically about the activity of ions versus water makes it more soluble. What about activity that makes it more soluble in sodium nitrate than in water?
Has like stronger electron densities versus like the polar.
Well, we really wouldn't talk in terms of electron densities because electron densities are usually like orbitals and that kind of stuff. And so we would talk in different terms for this. What terms would we talk for this? Ion pairing does what?
It reduces solubility.
Not reduce the solubility. I mean,
To result in higher solubility.
well, what was I talking about? Le Chatelet's principle there in that sense.
Change in concentration or change in volume.
Yeah, the change in concentration. How did the ion pairing affect the concentration of the product?
It dilutes it because there's more of other species.
No, not really. So, if you wanted to dissolve more silver chloride, you need to shift the KSP equilibrium to the right or to the left?
To the right.
To the right. How do you shift it to the right? No, you don't. We're not talking about resetting. We're just talking about the whole equilibrium. How does something shift to the right? Adding more reactant, but in this case the reactant is a pure solid, so nothing's going to happen. Or removing product. And so how did the uncommon ion effect, how did sodium nitrate remove product?
It reacted with the silver.
You know, if you ask me this question of how do you make silver chloride more soluble, we talked about this in terms of Le Chatelet's principle when we were talking about the qualitative analysis lab. And in qualitative analysis, I wrote the equations. In fact, that's equations for silver as a Le Chatelet shift, right? And then basically, it's the same thing that's happening with the uncommon ion effect. You know, Yeah, in fact, this person, I just grabbed one of these at random. This person says shifts left, shifts right, you know, that kind of thing. That's what we're talking about here. And so I mean, maybe not everybody caught it yesterday, but did we talk about lead iodide being more soluble in sodium nitrate? I thought we did.
Yes.
And if you don't quite understand the explanation for that, then make sure you try to get it before the test. So you should ask me about yesterday. What was going on with that, the uncommon ion effect. And so what was going on with the uncommon ion effect? Can somebody explain it to me? Just
We had other ions blocking certain ions from forming a precipitate
okay,
because of the ionic.
that's one way, but I talked about it in terms of Le Chatelier's, so explain it to me in terms of Le Chatelier's principle.
Well, I mean, if you have like other,
I talked about a shift right. Why did it shift right?
because the ions in the sulfate are consuming the products, which causes
Yeah, it's not a complete consumption, but what it does is those ions interact with the products, reducing the concentration of the free ions. So anything that reacts will increase the solubility. It's as simple as that. I can't say specifically because there's tons of things that can react, including sodium nitrate. Those don't actually go through a chemical reaction, but they go through some kind of physical process which lowers the concentration. But if you had something that would chemically attack those, like ammonia, then obviously it's going to shift to the right. That's what we did in lab. That's how we got it to dissolve. We added ammonia, right? And that made it dissolve. And so that's an easy way to do it. Anything that decreases the product concentration. It could be uncommon ions, doing the ion-ion attraction thing, or it could be something that actually attacks this. Like what would attack chloride?
sodium nitrate.
Well, those don't really attack it, but silver, what attacks silver is ammonia. This is what I wrote on the... Do you guys remember writing this equation out for the qual?
Yeah.
Yeah, ammonia is going to attack the silver ion, thereby decreasing the silver ion concentration, shifting this to the right. So what else attacks? That's what will dissolve silver chloride. It's an easy thing to do if we have other things that will attack it, right? That's it. So this is the whole, I got a question about the whole concept of KSPA and KSPF are exactly this. KSPA, rather than writing it like this, I could have written this and in fact I did. In class, I wrote this as a KSPF. Do you guys even have that in your notes? So maybe I did this one as an example, maybe I did a different one, but do you have an example of a KSPF equation in your notes?
Copper hydroxide.
All right, copper was it?
Copper hydroxide.
Okay, copper hydroxide. Not this one, but copper. Let's take a look at that. Rather than writing it like Le Chatelier's like this, we could write it like this, right? More quantitative so we could do calculations. This Le Chatelier's business is okay for qualitative, but if we want quantitative, what will attack? Obviously acid will attack hydroxide. So how can I get copper 2 hydroxide to dissolve? I just attack the hydroxide with acid. I attack the hydroxide with acid. This whole thing's going to shift to the to the right, which means it's going to dissolve and make it more soluble in acid, right? Well, rather than doing that in terms of Le Chatelier's, I'm going to attack this with H+, I'm going to form water, the whole thing's going to shift, right? All right, this is how we did it in lab because it's all qualitative. When we do this quantitatively, I want to do this as an acid. Acid attacks what? Acid attacks hydroxide to form water. I have 2 hydroxides, so I'll just add 2 acids in this case because each hydroxide is the same. So I get something like this. Right? If I combine these two equations, then I have what's called KSPA. Remember I called KSPA acid attacks the equilibrium. What does the acid attack in the equilibrium? That's called KSPA, right? And so KSPA is showing how acid will act. And then just add these two up. Is it okay to do a combined method, or do I have to do stepwise or simultaneous? Combined is okay. Why? Why didn't I use combined in the earlier chapters? Why just this chapter? Somebody tell me the restriction for combined method. It's okay if... Yes. This is small, this is large, which means that the intermediate, what is the intermediate? In this equilibrium, when I do the combine, something cancels out. What cancels out? Hydroxide. Is that okay to cancel out hydroxide? It's okay if we produce very little and it's consumed significantly. And so this is why small, large works. Right? Small, step 1, large, step 2 combined is okay. And so we combine these. What do we do? You know, this is what? This is KSP. This is what? This is KW, but it's not KW. It's the reverse of the KW. And in fact, it's doubled, so it's got to be 1 over KW squared. Something like that. Does that make sense? And then when we combine it, you multiply the K's. This is called KSPA, you know, the combined equation. Yes? All right, but the same thing. We don't have to have acid attack. We could have other things attack. What else would attack this? Ammonia plus ammonia. This second equation is called what? KF. This is called KSP. F. Same concept. Same type of thing. I mean, this is... The KSPA and the KSPF are similar. You know, it's just one is acid attacking, the other is complex formation. But they both accomplish the same thing. This one is going to make it shift to the right. And we don't have to deal with multiple equilibria here. We just add these two equations up and multiply the K's, and we get KSP. Yeah. This is a KSPF. And so this is a lot easier than doing multiple equilibria, but there's a species missing here. What is missing? What species is missing? The copper. Is that okay? Well, not really, because copper's there, but we know, assuming that there's no copper is okay, because the amount of copper we expect is very little, right? The amount of free copper. We expect all the copper to be complex because KF is usually very, very what? Large. And so this is KSPF. This should be familiar, I hope. You know, KSPA and KSPF. These are both very important for chapter 18. All right, what else? So what else will dissolve it? Well, anything that attacks hydroxide, HCl, HBr, HI, anything that attacks copper too. You know, you got to look at what attacks copper too. Copper 2 being attacked is more complicated because it's a Lewis acid-base reaction, right? Lewis acid-base reactions, you don't have a simple chart like Bronsted. And I've been talking about this, that Lewis is a lot more difficult to predict because you need a lot more theoretical knowledge. And so usually you just look those things up in a chart, right? You know, like how many ammonias attack copper? I don't know. You look it up in a chart. What else likes to attack copper? Lewis bases. Look it up in a chart because ammonia doesn't attack everything. You saw that in the qual lab. It attacked nickel, but did it attack aluminum? Did it attack chromium? Did it? And so, you know, the first step in understanding this is to just write it down, you know, once. Maybe it registers, maybe it doesn't register. You know, you did write it down. You know, a nickel plus the ammonia, 6 ammonias gave you the hexamine complex. But what about the chromium plus ammonia? Did you get a complex? And so that type of stuff we look up. I don't expect you to have it memorized. And so there are lots of things that will dissolve silver chloride, not just ammonia. All right, what else do you guys have questions on? So the question on the number 16, you know, from the practice test, that's calcium sulfate. You know, I did that. Did I do that one in class, in lecture?
No.
Which one did I do in lecture?
Calcium carbonate.
Calcium carbonate? It's the exact same setup.
Yep.
Exact same setup. You know? It's a KSPA. Like this. That's it. Yeah, I mean, we have to look at how it is there. Any other questions from the practice test? Uh-huh.
When you do 14, the solution is made up of 0.100 molar silver and 0.100 molar chlorine. What percent of silver remains after precipitation?
The chlorine or chloride, because there's a huge difference.
Chloride.
How do you do it? Actually, can somebody? How many people got that problem?
Yep, this one.
Number 14.
Do like the KSP, which they gave it to you in the beginning in another problem. AgCl. It's 1.8 times 10 to the negative 10. And then you do the concentrations of Ag and Cl, which is 0.1 and 0.1, which comes out to S squared. This is X and X. If you do an ice chart.
How did you approach it yourself? You know, that's right. You say.
I didn't really know how to start, so that's the worst part for me, I guess.
Well, where would you start? I mean, did you give it an attempt to go?
Not really.
Not really. Basically, then you would just set up an ice chart. You know, what was it? AgCl?
Yeah.
The precipitate. You set up an ice chart. Here. And so just set up the ice chart, and then you could work at it from just, it's just a standard ice chart. You could just do it. You plug in your initial concentrations there and just solve. You know, this way is called precipitation. This way would be dissolution. And so what were the concentrations?
0.100.
0.100? 0.100? And this would be minus minus x, you know what x is? X is called that would be precipitation. And so this is one way. You could do it like Jonathan, or you could do it like this, you know. There are multiple ways to solve this problem. This is just a standard ice chart setup.
And the new KCP would just be the reciprocal of 1 divided.
Well, yeah, you could do it that way as well. I mean, you know, there are different ways, but I don't want to confuse you because this isn't the way I do it, to be honest. But you know, if you don't know where to start this one at all, I don't want to confuse you. You just do it as set up. It works. It'll work. So just do it like this. But you got to figure out, you know, how x, you know, what x is. If x is the percent precipitation, then what is the percent remaining? You'll have to figure that one out.
Are we doing a lab today?
We aren't doing a lab today. We're just going to go just take the test. But I need to lecture first on the lab from last time. So basically, just go through this. It's just your standard. This one is not too difficult. Did you hear anything else? All right. If there are no other questions, you know, give this one a try, and you guys give this one a try. See where you get stuck, and then we'll go through it from there. I need to talk about the lab we did last time. We're going to go into the computer lab. I'm not going to have that much time to talk about what we're doing with the data. And so I just want to talk about what we're doing with the data now from the kinetics lab. When we did the experiment one of the things we did was this. Normally when we start a kinetics lab, we have a time 0. But time 0 is, you know, the beginning of the reaction, right at the start. But what happens with our kinetics lab is when the first drop of crystal violet hits your sodium hydroxide solution, it starts to react. And so immediately it starts reacting, but the problem is did we get an absorbance reading there at time 0? No, because what happens is we need time to mix it up and we need time to put it in the cuvette. And so the instrument 0 is not really our time 0. This is the instrument time 0. And there's about a minute delay, or more or less, right? There's some type of delay here. And so all this data is missing here. And then finally, once we get it into the machine, it starts to collect data. And we generate our plot. From this, if we're missing this data, can we still determine if this is a 0 order, first order, or second order? Yeah, it's not going to be any big deal. So if we miss some of this, you know, the basic shape of the curve should still be the same. In fact, it is going to be the same. And we can see, you know, oh, this might be a first order, it might be a second, or it might be 0. And so what we're going to do in the computer lab is we're going to make 3 plots up. You know, starting with our instrument 0 here. We're going to make an absorbance versus time. Absorbance is directly proportional to the concentration. And so essentially this is a concentration of CV versus time plot. And we can see how the concentration of the CV varies with time. Here. Okay, if this plot is linear, then we say it's first order. However, if this plot is curved, sometimes it's difficult to see. You know, is that a first order or is that a second order curve? And to help answer that, we're going to make two more plots in addition to this. We're going to plot the absorbance versus T. We're going to plot the log of the absorbance, or the natural log of the absorbance, either one, versus T. And we're going to plot the 1 over the absorbance, so 1 over the concentration versus T. All right, this is going to make it a lot easier than trying to eyeball the curve. You know, is that curve first order or second order? If the curve is first order, then the log of the absorbance versus T will be linear, a straight line graph. If that curve is second order, then the 1 over the absorbance versus T will be linear. Only one of these plots will be linear. And so based on which one of these three plots is linear, we can determine the order with respect to CV. In other words, we can determine M. And so this is equal to K times the CV plus to the M, hydroxide to the N. Here. All right, once we figure out what M is, then we need to figure out what N and K are. And so it's pretty quick when we do this to determine M. All right, then we went to experiment 2. In experiment 2, we had the same type of thing happen, where the first part of the data is missing. Actually, let's write that over here. But that's not a big deal. We can make the same three plots, absorbance versus time, ln, or log of the absorbance versus time, 1 over the absorbance. And what we should see is we should see agreement between experiment 1 and experiment 2. If experiment 1 says it's first order, then experiment 2 should have the same result. It should just be confirmation of what we determined from experiment 1. That's for M. The reason we did experiment 2 was to determine N. How do we determine what N is? Here. So, well, going back to M, over here, the CV concentration is changing here, but what's happening with the hydroxide concentration? The hydroxide is changing negligibly because we made the hydroxide concentration so large it stays relatively constant. And so when we look at this, the only thing that's really impacting the rate is the change in the concentration of CV. And so what we're going to do is we're going to combine these two, K and the hydroxide, and call it K prime. This is where K prime is equal to K times the hydroxide ion concentration raised to the n power. And so that's going to be a new constant. And so we can see that the rate will just solely be dependent on CV concentration. Now for experiment 2, what we should do is we should make it pseudo n order instead of pseudo m order, which we did over here. But we didn't do that. The difference between experiment 1 and experiment 2 is this. We just doubled the hydroxide. We left everything else the same. And so the CV is the same between experiment 1 and experiment 2. The hydroxide's been doubled. Well, if we double the hydroxide, that's called the method of initial rates. The method of initial rates says, let's keep everything else the same and double one of them. And so if we double the hydroxide and the rate doubles, then it's first order. If we double the hydroxide and the rate quadruples, it's second order. If we double the hydroxide and nothing happens to the rate, then it's 0 order. But it's not just any rate, because the problem is the rate might be changing all along here. And so when we use the method, it's called the method of initial rates because we want to compare the initial rates. There's a major problem here. What is the major problem? The major problem is the initial rate is not here. The initial rate is here. The initial rate is here at the true time 0. But do we even have any data at the true time 0? And so we can't even determine the initial rate because there's no data here. And the same thing with this experiment. We don't have the initial rate because we never took any data right at the beginning of the experiment. And to determine the initial rate, you know, we'd need data here. We'd either make the tangent to the line, so we'd need a curve here, or we take the first 2 data points. If we take the first 2 data points, then usually less than 5% reactions occurred, and we just use that as our initial rate. But we don't even have the first 2 data points. We don't have the tangent. And not only that, initial rates are very hard to determine accurately because there's always going to be quite a bit of experimental error. You know, let's say the first data point had an error bar like this. You know, there's some random fluctuations that can make it this big or this small. That means your initial rate will be hugely different. You know? And so this is a problem here. Well, what if we just take our machine times 0? You know, when we push the start button on the SpectroViz, or not SpectroViz, but Logger Pro 2. When we push the start button, did you wait a measured amount of time? Let's say you waited a minute and a half and then pushed the start button in experiment 1, and then waited the exact same amount of time here in experiment 2. Did you do that? No, we didn't do that. And so how are we going to figure this out then? Well, the way we're going to figure this out is this way. We're going to use a modified version of the method of initial rates. Okay, the method of initial rates is we just take like the rate 2 over rate 1, you know, assuming usually we like to have the bigger rate on the top, the smaller rate on the bottom. So we'll just say bigger here, and smaller here. And so normally we see, did the rate double, 2-fold, 4-fold, or stay the same? As far as the ratio goes. And then we look here, well, the rate of 2 is just going to equal K times the concentration of CV 2 to the M, hydroxide 2 to the M. And so we just plug in the concentrations we use for run 2 here over K, CV, run 1 to the M, hydroxide, run 1 to the N. Here. Both of these were pseudo M order. And so what we can do is we could just take the hydroxide here and combine the constants. And so this is K times hydroxide 2, which we'll call K prime 2, times the CV plus, and run 2 to the M. And then we'll do the same thing here. We'll combine the constants. And so we'll make a new constant, K prime 1 times the CV plus 1 to the M. Now, these two Ks are the same, actually. But are these two Ks the same? Is K2 prime and K1 prime the same thing? No, they aren't, because the hydroxide concentrations are different. You know, in fact, K2 prime is going to have double the hydroxide, so it's going to be twice as big. How about CV? Was the CV in run 2 the same as the CV in run 1? The answer is yes, because it was 10 milliliters in each. And so the CV turns out to be the same. And so what we have here is this. Rather than figuring out what the initial rate is, because that's what we use, right? We don't just pick any old rate. We don't say we're going to pick a rate down here and compare it to a rate up here. That doesn't work. If the rate's always changing, we've got to be consistent, right? Pick the same rate. And so this is why we use the initial rate, because the initial rate will be consistent, a valid comparison between the runs. And so here we don't need the initial rates, fortunately. Instead, we're going to use the ratios of K2 prime over K1 prime. But where do we get these from? Well, these come from the slopes of the graph. Remember our K analysis? Our K analysis is trying to figure out which of those graphs has a constant K. And so K2 prime is the slope or the negative slope of the linear plot. Only one of the three plots will be linear. That'll be it. And then K1 prime will be the slope of the linear plot for run 1. The advantage to using K here is this. One, we don't have to worry about the initial rate. And two, we're using all the data. Because when we make a plot, we tend to average out all the data. And so let's say the plot is like this. And there's going to be random fluctuations due to random error. And what we'll do is we'll draw the best fit straight line through our data. And when we do the best fit straight line, that averages the data out. And so this is, when we have a line like this and we measure its slope, that slope is the average of all the data here. And so this will be much less prone to error. All right, now what do we do with the, what do we do with it? In this case, the negative of the slope is equal to K. K prime. So what we're going to do with these is this. We're going to look at these two equations here and combine those. And so we're going to get K2 prime over K1 prime is equal to K times the CV plus for run 2 times the hydroxide for run 2 over the K for CV plus run 1 hydroxide for run 1. Okay, the CV is raised to the m power, the hydroxide is raised to the n power. By this time we should know what m is, but it's okay because it's going to cancel out here. And so K's cancel, these aren't K primes, these are just the rate constant, and the CV's cancel. And so the ratio of the K primes is going to equal the ratio of the hydroxides here raised to the n power. And so let's simplify this. I'm going to put the hydroxide for run 2 over the hydroxide for run 1, this whole thing raised to the n power. Now the hydroxide in run 2 was double the hydroxide in run 1. And so we could just go ahead and substitute that in. The hydroxide in run 2 is equal to 2 times the hydroxide in run 1 divided by the hydroxide in run 1 raised to the n power. Hydroxide in run 1 cancels out, and so this gives us 2 to the n. All right, so once we have the ratio of the K primes, then we solve for n. And that should give us n. Okay, now up to this point we should have m and n. The only thing missing is k. And we don't want k prime necessarily, we want k. But it's easy to get because k from run 1 is just equal to k prime 1 times the hydroxide. Oh, actually, wrong. Divided by the hydroxide in run 1. Okay, and from run 2, we have k is equal to k prime 2 divided by the hydroxide from run 2. And then we'll just get k average. K average is just k from run 1 plus k from run 2 divided by 2. They should be the same number. The k primes aren't going to be the same number because of the factor of the hydroxide ion concentration. But the k should be equal. All right, so our ultimate goal is to get the rate law. The rate law is just going to be the rate is equal to K. This will be K average. And so we have this number from there times the CV plus concentration to the M. We have this from the plots, analyzing which one's linear, times the hydroxide to the N. And we calculate from using the modified rate, method of initial rates. Okay, and then this is it. This is what we're after in this experiment. All right, any questions with this? Did you guys have any other questions? No? All right, I'm going to stop it here. You can take a break.